Hello everyone. So in this problem solving session, we're going to consider this problem right here. Consider the following three vectors. So you're given three vectors A, B, and C, and those vectors are expressed in terms of Cartesian basis vector system, which is x hat, y hat, and z hat, all of which are unit vectors along the x direction, y direction, and z direction respectively. Now the question is, the question is actually a two-parter. The first part talks about finding out the volume formed by these three vectors. So there are three vectors. We know they create a parallelepiped or parallelepiped. It doesn't matter how you say it. So it forms a parallelepiped, and the question is, we need to find out the volume of that parallelepiped. So that's the first part of the question. The second part talks about interpreting the result geometrically. The first part is actually the easier part, and the second part is the harder part because it takes quite some time to comprehend, but it's not that difficult. Once I explain it to you, you'll understand what it means for what the result to be interpreted geometrically. Okay? So let's start the system. So the first thing we should know in order to solve this problem is that if we're given three vectors, which are A, B, and C, then the volume that has been formed by these three vectors can be expressed in this form: A cross B dotted with the vector C. This is what we call a triple product of vectors. So this is exactly the combination how it should play out. You'll notice that if we would write it the other way around, so for example A cross then B dot C, this thing wouldn't work, would it? Because B dot C is going to give you a number, so this is a number, but A is a vector, and you cannot take cross product between a number and a vector. The cross product must be taken between two vectors all the time. Here, this is consistent in this expression right here. We have A cross B, so it's going to give you a vector in return, and then you dot it with C, which in return is going to give you a scalar. And this thing over here is called the triple product, which denotes the volume of the parallelepiped. So this is going to be the volume of the parallelepiped created by A, B, and C. Now, something very interesting you should notice as well is that this thing here is the same as taking this combination right here, C cross A dotted with B. And not only that, we have another combination which is exactly the same in terms of the result, and that is B cross C dotted with A. As you can notice, we are always taking the cyclic combination. So A, B, C, it creates a cycle. B after A, and then C after B, and then A after C, and it goes on. And as long as you follow that cyclic order, then it's always going to give you the same result. However, if you alter one of the cyclic orders, so for example, if you take A cross C dot B, that's going to give you negative of what we would get from the original result. Now, the question would be, what does the expression or the expansion look like in terms of the components in Cartesian coordinates? Because after all, in the problem that's been given or presented to us, the vectors are written in terms of the Cartesian coordinate, and so we better write our result in that form. And that is rather easy to see. Just allow me a minute to show you the result. So here we go. So here, once again, we write down the product. In terms of the components, this is what it should look like. So we know that in Cartesian coordinate, the cross product would look like a determinant or behave like a determinant because of its antisymmetric property. So defined is the following. So we have x hat, y hat, and z hat in the first row, and then we have the components of the vector A. And on the last row, we have bx, by, bz. Okay, so that's something that we all know. And if we take the dot product with c, so this is going to be a vector a cross b. So the coefficient of x hat is going to be this small determinant, and then, you know, in the usual rule, you have the coefficient of y hat, and z hat comes in the natural cyclic permutation order. So we have to dot it with what? With the vector c. Now c has to be written in terms of the Cartesian basis vectors. So we write cx x hat plus cy y hat plus cz z hat. All right, so we have that. Now what's going to happen if you take the dot product, then only the dot product between the x hat and x hat would survive, y hat and y hat would survive, and z hat and z hat would survive, and all the cross terms are going to go away. So these, in this determinant, these basis vectors are going to be replaced by the coefficients of their corresponding basis vectors in this expression here. So what that means is that in the place of ax, ay, and az, and bx, by, and bz, these parts remain the same, and the first line, the first row, is going to be replaced by cx, cy, and cz. Okay, does that make sense? And then from this you can confirm the other combinations we have written for the triple product do conform with this formula. So for example, if we write ax, ay, az, bx, by, bz, and cx, cy, cz, all right, then this and the expression on the left are going to be the same. Why? Because this is going to be b cross c dotted with a. Okay, so in the upstairs we have written that this one here and that one here are going to be equivalent, and this can be seen from these expressions right here, because this determinant right here can be shown to be equivalent to this determinant right here by simply altering the rows. Okay, so for example, in order to go from here to there, I should take this row, second row, and replace it with the first one. So you get a minus sign, right? An extra minus sign. And then you take this row, which is now the second row, this one, which is now the second row, to be exchanged with this row right here. Okay, so that's the third one. So B goes to number 2, A goes to number 1, C goes to number C. And on the second step, you're going to find another negative sign. So altogether, you get a plus sign. And the determinant has turned to this one as well, without any change whatsoever. Okay, so now that you have understood this, we have also found a formula which comes handy in the settings of our problem. So this is going to be the determinant in terms of the problem we have been given, and rightfully, as you will find out, the result turns out to be 0. So wait a second, what's going on? This is going to give us 0 volume. I think with the picture would help. Let's just see. This is the figure for this triple product A cross B dotted with C. Okay, now as you'll notice, what is going on is, well, by the way, I should make a disclaimer. This is not my picture. I've just taken it randomly from internet. Looks good. So whoever created it, kudos to them. Anyway, so this surface here, its area is given by the magnitude of A cross B. Okay, the magnitude of A cross B, which is AB sine of whatever the angle we find here. Let's call it theta, so AB sine theta. And then we see that this is C, right? This is C vectors. All of these are vectors. So when you type, you just type it in bold letter in order to show that it is vector, but in order to be safe, we are going to play nice and put arrows over the vectors. So what's going on? So A cross B, so this is going to be this, right? The bottom surface right here. And then in order to find the volume, you need the height. And I'll notice if this is given by phi, then this height here, okay, is given by c cosine of phi. Do you know why? Because that's the adjacent side. So you notice these guys who have created the picture have shown us that this height right here, the adjacent side, is going to be cosine of phi, which is very correct, which is exactly what we have written. Because this length right here, right, this one, is going to be the same as this one because they're parallel and they're both perpendicular over the same surface. Now the question is, what does it mean for this parallelepiped to have zero volume? So you can imagine this to be like a juice box, as we have discussed many times in our class, and you squash it, you crush it. What does that mean? It means you change this angle, right? You change this angle and you make this angle 90 degrees. Okay? What does it mean? It means that C, this vector C, is now on this plane over here somewhere, totally on this plane. So C is lying in the plane created by A and B. So what's happening is that now C can be expressed in terms of some number, x times A plus y times B, where x and y are simply real numbers. Okay, they can be any numbers. You can find them out by doing dot products or by doing simple algebras. But the crux of the matter is that in order to have zero volume, C has to be in the same plane as A and B. And this thing right here is what we call a linear combination. Okay, so for example, if I have two vectors A and B, and if I write 5A plus 2B. So what we have done is we have created a new vector which lies in the same plane as A and B, and this new vector can be completely characterized by A and B along with the two numbers, and these two numbers are called the coefficients of A and coefficients of B respectively. So this is a new vector, right? But this is dependent on A and B. Okay? In contrast, so for example, x hat and y hat, they cannot create, no matter what number you multiply x hat and y hat with, they cannot create z hat. Okay, this is simply not possible. Right? So that means z hat is linearly independent of x and y. Whereas in this scenario, as we can see, this C is linearly dependent on A and B. Now, of course, if C is linearly dependent on A and B, we can also say A is linearly dependent on C and B. Okay, so some number, for example, probably minus 2 plus 4 or something else, probably, right? So it's always a set of vectors that are linearly dependent or independent. Okay, so for example, if we take x hat and y hat, these two, and z hat, these set of vectors are linearly independent, because no matter which numbers you multiply the two vectors with, you cannot make up the third vector, okay, by taking linear combinations. So for example, some number p times y hat plus q times z hat. Then most definitely, without doing the math, I can say p and q is going to be 0 because x is independent of x hat and z hat. Do you understand? So for example, if I take x hat equal to this, I can take x hat dot y hat. So obviously this is going to give us 0, right? And then here you have p times y hat dot y hat plus q z hat dot y hat. Now this guy is going to be 0, this guy is going to be 1, so p is equal to 0. right? Because 0 equal to p plus 0. So what other option does p have? So p is bound to be 0. Similarly, you can also show that q is also going to be 0. So p and q are identically 0 because x is independent of y hat and z hat. Do you understand? That's why this set is called linearly independent set. However, so for example, had I chosen this set, x hat, comma, y hat, and then 2x plus 3y hat, this set is linearly dependent. Okay, do you understand why? Because you take any vector. So for example, I could take x and call this vector, for example, w. I can express x with the help of y hat and w. Do you see how? So let me write in this way: x hat equal to some number p y hat plus some number q times w. So p y hat plus q, in the place of w we just substitute the expression for w, which is 2x hat and 3y hat, and we can simplify it a bit. So p plus 3q, okay, times p plus 3q times y hat plus 2q x hat. And in the same process, now find out what these numbers are. So as you'll notice that p plus 3q is going to be 0, right? Because you do not have any y hat in the left hand side. So the only way you can equate the left hand side with the right hand side is by taking the coefficients to be equal. So this is going to be 0 and 2q is going to be equal to 1. So q is going to be 1/2, and consequently p is going to be negative 3/2. Okay, so do you notice we can express x as a linear combination of y hat and w because x hat is dependent on them. So back to our own problem. Because we have found the volume is going to be 0, it's quite clear that C is on the same plane as A and B. So as an exercise, so that you can understand this better, if C can be written as a linear combination, so for some number A, so this is some number times A vector plus B times capital B vector, if this is the case, then use these expressions in order to find A and B. And this is what I'm going to bet, okay? You'll find that A and B are not going to be 0. Because if they were 0, then they would create a volume and the volume would be non-zero. But because A and B are identically non-zero, so that means C is dependent on A and B, and that's why it lies on the same plane as A and B, and that's what makes the volume 0. If this seems to be very complicated, I suggest you watching this video again, and if you don't understand even then, I suggest you get in contact with me and possibly book a consultation time face-to-face. Best of luck, and I'll see you later.